In our last lecture, we examined a two-mass system consisting of two masses connected by a spring with a force input. We found the transfer functions, and we sketched the poles and zeros in the complex plane. In this lecture, we handle a second two-mass system. We'll now look at another two-mass example. And this one is similar to the one we just did, except there's one more spring, this time attaching mass M1 to a wall. So we've got spring K1 attaching M1 to a wall. We've got masses M1 and M2 sliding on a surface with no friction. And M1 and M2 are joined by spring K2. We have a force, as in the previous example, acting on mass M2. And we'll label the displacement of M1 away from its equilibrium position when both springs are undeformed as x1, and we'll label the motion of M2 also from the undeformed equilibrium as x2. Positive input force Fi is to the right. The output for this example will be the motion of mass M2, which is x2, and we label this y. I'm going to let you figure out what the free body diagrams for M1 and M2 are, and also work out what the forces are that are exerted by springs K1 and K2 on masses M1 and M2, and the relationships between those forces and the displacements x1 and x2. Once you've done that, you'll get the differential equations. And from the differential equations, you can Laplace transform and find the following algebraic equations. So we'll do some algebra here, and I won't bother going through all the steps, but in the end, I'll find the relationship between x2 and Fi, shown at the bottom of this page. Then I'll divide the left and the right hand side by the term in the curly bracket. That'll bring it over to the other side, allowing me to solve for x2. This yields the following transfer function between input force Fi and output x2. We have a second order numerator divided by a fourth order denominator. And I'll point out that all four poles of this transfer function, the roots of the denominator, are imaginary valued. This transfer function also has two zeros, and they are imaginary valued as well. And we can actually explicitly give them. They are plus and minus j square root of k1 plus k2 divided by m1. The placement of the poles and zeros in the complex plane will look as follows. We'll have two sets of complex conjugate poles on the imaginary axis and a pair of zeros between them. This property of the zeros appearing between the poles is referred to as interlacing. Each of these sets of poles corresponds to a natural frequency. So this fourth order system has two natural frequencies. Let's call these two natural frequencies omega 1 and omega 2. Then one set of poles is at plus and minus j omega 1, and the other set of poles is at plus and minus j omega 2. Note that unlike the previous example of a two-mass system, there are no poles at the origin of the complex plane. Recall before that we had two poles at the origin, and I said these corresponded to the rigid body mode of that system. There are no poles at the origin here, so there are no rigid body modes. A rigid body mode would correspond to the translation of the entire system across the tabletop. Since this system has spring K1 tying M1 to the wall, there can be no rigid body motion that persists across the tabletop, and therefore there is no rigid body mode. The only modes we have here are vibration modes, and the two natural frequencies correspond to two vibration modes. The oscillatory vibration mode for plus and minus j omega 1 would consist of characteristic modes e to the plus j omega 1 t and e to the minus j omega 1 t. In a similar fashion, for the poles at plus and minus j omega 2, we have characteristic modes e to the plus j omega 2t and e to the minus j omega 2t.